In this video, I want to quickly walk through the mechanism for a reaction called the Claisen condensation. And this way, as we talk about it from the perspective of synthesis in future videos, you'll sort of have an understanding of why certain things are being added and why certain products are being obtained. So the idea behind the Claisen condensation is that it's really just a nucleophilic acyl substitution. If you think of this molecule here as this one here, then you'll notice that this leaving group, I mean, after all, this is an ester that we start with, and you always start with an ester in the Claisen condensation. Esters are carboxylic acid derivatives, and whenever you see carboxylic acid derivatives, you want to see that group attached to the carbonyl carbon as a leaving group. And so that group was changed with this other group. So you could sort of see how this leaving group left. First, that leaving group left, and this nucleophile came in. And that's where, now when we say nucleophile, that's where this nucleophilic acyl substitution reaction connects with this alpha carbon chemistry chapter, because the nucleophile is going to be an alpha carbon. So we'll have to treat the original molecule with a base in order to turn the alpha carbon into a nucleophile, but from there it's just a nucleophilic acyl substitution, like we practiced a whole bunch in the carboxylic acid chapter. Okay, so the last thing is you'll see why you add this water at the end, and or the hydronium at the end. And one important thing is to note that this is done at a relatively low temperature so that it doesn't hydrolyze the ester here. Okay, so the general idea in the Claisen condensation is you're having more than one ester stick to each other. That's the condensation. Multiple molecules are sticking to each other and ejecting a small molecule as they do that. That's what a condensation is. And so here we're having multiple esters stick to each other, as opposed to the aldol condensation was where we had an aldehyde or a ketone sticking to each other. We're going to use the nucleophilicity of the alpha carbon. Okay, so let's say we have our original ester. How does this happen? Oops, we have this original ester here. And you want to treat this with a base. Now you'll notice we're not treating it with sodium hydroxide or with LDA, lithium diisopropylamide. Those are the two bases we've talked about so far in this chapter. We're not treating it with those. We're specifically treating it, not with sodium ethoxide necessarily, but we're specifically treating it with whatever the base matches the ether of the ester. So, for example, if this were a methoxy group, then you would want sodium methoxide. If it were a propoxy group, and there is an abbreviation for that, it's OPR, but if you had a propoxy group, excuse me, then you would want sodium propoxide. So you want to treat this with whatever base is in the ester. And the reason for that is when you have this ethoxy group, or this, in general, alkoxy group, that can act as a base to steal the alpha hydrogen, as we're going to draw in just a second, but it can also technically act as a nucleophile. So a strong nucleophile could attack the carbonyl carbon and do a nucleophilic acyl substitution. So long as this group is the same as the ether group, that competing reaction won't change the overall molecule. So it's important that this matches that so that that competing nucleophilic acyl substitution doesn't change the overall molecule. So while that nucleophilic acyl substitution is competing, another reaction is happening. The alkoxy group acts as a base and steals the acidic alpha hydrogen. The electrons snap back onto the carbon there, the alpha carbon. So what we have happening in this first step is a proton transfer. A proton transfer to create the nucleophile on the alpha carbon, to change the reactivity of that alpha carbon. Okay, so after that step, we will still have our ester, but the alpha carbon will be a nucleophile. Okay, now this is where, so that's so far very standard for this chapter. And all we need now is another molecule of this ester, and we're just going to do a nucleophilic acyl substitution. So that from now on, this should look really similar to the carboxylic acid derivative chapter. Our nucleophile comes in, attacks the carbonyl carbon, which is slightly positive. The pi bond breaks, goes onto the oxygen, and we're going to get our famous tetrahedral intermediate. And what we have here is nucleophilic attack. Remember, in substitution reactions, you always need nucleophilic attack. That brings the new thing in, and loss of a leaving group. That gets rid of the thing you're substituting for. So now we're going to have 4 carbons connected to each other. Let's number them just so that it's easier to keep track. So we have the ethoxy group, then we have carbon 1 and 2, the carbonyl on carbon 1. And then we're going to have 2 more carbons, carbons 3 and 4. So carbons 3 and 4, I'll worry about what's on those after I draw the carbons themselves. On carbon number 3, we want to have a single bond to an oxygen. The oxygen is going to have 3 lone pairs and a full negative charge. And we also want a single bond to an ethoxy group. Okay, so this is the new bond that we formed here. That's the bond, and maybe I'll draw it in purple. Those are these purple electrons there. And actually, let me do that. Just so we can visually see what's happening. These electrons created this new bond. This was the carbonyl. All right, so now we have our tetrahedral intermediate. That negative oxygen flapping in the wind can snap back down, kick the ethoxy group off. So that's the second essential step in any substitution reaction, loss of a leaving group. And what we have after that step is our ethoxy group leaves, and we recreate the carbonyl on carbon number 3. And that looks a lot like our product. There is one problem with this. There are actually 2 more steps in this reaction. So far we haven't explained why we need to add this H3O+. So let's talk about that. Remember, we still have base in this solution. We still have ethoxide, or whatever alkoxide we used, whatever matches the ether in the original molecule. And we also have a vulnerable hydrogen. We have an alpha hydrogen. This hydrogen is alpha to 2 carbonyls. So it's really acidic, because if this base steals that and the electrons go onto that carbon there, then the electrons are allylic to 2 pi bonds. So they're spread out in parallel p orbitals over all 5 of those atoms. And so that's really stabilized. And because that conjugate base is stabilized, the original hydrogen is it's not difficult to make it leave. And so, in other words, it's very acidic. So this is technically what we have if we just use the first step. And that's why we have to add H3O+, just to do a proton transfer. Now, it's crucial that this is done in a separate step. You don't want to mix all of this together, so when you when you write the recipe, you want to make sure that there's a 1 and a 2 here. Because if you put a base and an acid together, they're just going to neutralize each other. They won't react with your molecule. They'll react with each other instead. So after you're finished doing the sodium ethoxide step, you'll do this last step to protonate that alpha position. It's crucial that you do this at low temperature so that the ester does not hydrolyze. You'll remember you drew the mechanism for the hydrolysis of an ester in H3O+. So you just want to make sure you keep this cold so that doesn't have enough energy to do that. And you just do the proton transfer, and so you end up with the beautiful product that you get above. So the way you want to, or there are a couple things to notice here. First, what's the point? Why do you do a Claisen condensation? You do a Claisen condensation to make two esters stick together. What is the Claisen condensation? The Claisen condensation is basically a nucleophilic acyl substitution reaction, where you have your original ester, but the leaving group, the ethoxy group, leaves, and the nucleophile that comes in is the alpha carbon of a second ester. So that's the concept here. And when you do that, you want to first treat it with a base, make sure your base matches whatever your leaving group is. And then after you're all done with that base, you would do an acid water wash at a low temperature to make sure you don't hydrolyze the ester.